Lecture 27, Thermoelectric Devices. So in this lecture, we will learn about the operation of thermoelectric devices. In a previous lecture, we have already learned that in a concentrated solar power plant, we can store solar thermal energy in molten salt in a storage tank. This is a very unique advantage of CSP power plants compared with photovoltaic plants, because in a CSP plant we can use the thermal energy in the molten salt and use it to generate electrical power at night time when the photovoltaic power plants simply cannot work. So in this lecture, we will learn how this can be done. How can a concentrating solar power plant generate electricity directly from the stored thermal energy in the molten salt. Now, in order to generate electricity directly from a storage heat source at night time, we will need to use a type of semiconductor device called a thermoelectric device, or TE device. So the semiconductor we use in a thermoelectric device is the same kind of material we use to make a solar cell. In the case of a solar cell, we use the semiconductor silicon. So here we use a different kind of semiconductor material to make a TE device. A little bit of background information. The thermoelectric effect was first discovered by a German scientist called Thomas Seebeck in 1823. Nearly 200 years ago. And for this reason, the thermoelectric effect is also called the Seebeck effect. So the two names, Seebeck effect and thermoelectric effect, are the same. Now, a thermoelectric device can operate in two ways or two modes. In this course, we are interested in the power generation mode. In the power generation mode, we have a temperature difference between the two sides of the TE device. So one side is hot and the other side is cold. And because of this temperature difference, we get a potential difference or voltage difference across the device. And this voltage difference is what we use to drive an electric current through a load. A load could be as simple as a resistor. So in other words, we have an energy conversion process in a TE device which is directly from heat to electricity. So you can see how the thermal energy in the molten salt of a CSP plant can in principle be converted directly into electricity. Now, the other mode of operation for a thermoelectric device is called the Peltier effect, or the Peltier mode. And here we mention it briefly. It is the reverse of the Seebeck effect. So now we apply a potential difference or a voltage difference between the two terminals of the TE device, and what happens is that heat will flow from the hot side to the cold side of the TE device. And this is very important because nowadays this is used to cool down electronic devices like microprocessors and also optoelectronic devices like a semiconductor laser. Let us look at the physical principle behind the Seebeck effect in more detail. We will start with the simplest case, which is the Seebeck effect in a conductor or a metal. So on the top diagram of this slide, we show the electrons in a metal where the left hand side is hot and the right hand side is cold. And we should realize that the heat is flowing from the hot side to the cold side because of the temperature difference. The heat is in fact being conducted from the hot side to the cold side by the electrons in the metal and also by these fixed mobile ions. But here, for simplicity, we do not show the metal ions in the top diagram. We will simply focus on the electrons. So each of the blue dots represent the conduction electrons in a metal. The conduction electrons are free to move anywhere inside the metal. And that is why each of the blue dots has an arrow associated with it. And this arrow indicates the velocity of that electron. The velocity simply means the speed and the direction. So if you have a longer arrow, it means that the electron is moving faster. And if the arrow is very short, it means that the electron is moving slower in a certain direction. Now, if we look at the top diagram, it's clear that the length of the arrows on the hot side of the metal are usually longer than the arrows on the cold side. And that is because, on average, the electrons at the hot end of the metal has more kinetic energy, or in other words, they are moving faster than the electrons on the cold end. So it should be quite easy to see that at the end there will be a net movement of electrons from the hot end to the cold end. And this is in fact how the heat is being conducted by the electrons from the hot side to the cold side. So the main point here is the temperature difference across the metal will give rise to a net diffusion of electrons from the left to the right of this piece of conductor. So what will that result in? We can look at the next page and we can see that the diffusion of electrons from the left side to the right side will eventually give rise to a potential difference or voltage difference between the two ends of the conductor. Let's move back to page 32 and we look at the bottom diagram. So in this diagram, we are trying to show what's called a steady state of this piece of metal. So in the steady state, when there are no further changes, you can see that there is a higher concentration of electrons on the cold side than there are electrons on the hot side. And that is because you have this net diffusion of electrons from the hot side to the cold side. We can see the concentration is higher on the cold side by the density of these blue dots. And what this concentration difference in the electrons will give rise to is an electric field. This electric field is opposing the diffusion of the electrons from the hot side, and this is in fact the reason why you have no further net diffusion of electrons in the steady state. And it's important to realize that once you reach this steady state, you will have a net negative charge on the right hand side and a net positive charge on the left hand side. So this is the origin of the thermoelectric or TE voltage. Now the ratio of the voltage difference and the temperature difference is called the Seebeck coefficient. The Seebeck coefficient has another name, and it is called the thermal power. It's given the symbol of alpha. So we can use this equation to define the thermal power or the Seebeck coefficient. It is simply the voltage difference delta V across the conductor divided by the temperature difference delta T across the conductor. The unit for the Seebeck coefficient is therefore the volts per Kelvin. Notice that the Seebeck coefficient is a property of this material, and it is also temperature dependent. So how do we measure this thermoelectric voltage? Suppose we try to measure the thermoelectric voltage across the metal 1, which is indicated by this red line in the middle. And as we can see, on the left side, the temperature T, or T hot, is higher than the temperature on the right hand side, which is T cold. Now, in order to measure the thermoelectric voltage, which arises from this temperature difference, what we must do in practice is to use another metal 2, a different metal 2, to contact metal 1. So in other words, if we want to measure the thermoelectric voltage across metal 1, we must use another metal 2, to form 2 contacts or 2 junctions with metal 1. The metal 2 is usually the metal platinum, or PT. And what we usually do is to let one junction to sit at a reference temperature such as 0 degrees C. And if we do that, the voltage that we measure across the 2 terminals of this setup, or the voltage V, will be proportional to the temperature difference between T hot or T cold. And since T cold is a reference temperature, we can use the voltage V, which is measured by this thermocouple, to measure the temperature of the hot junction. And this is in fact an important application of the thermoelectric effect. Now, why do we need to use a different metal to measure the thermoelectric voltage? It's because if metal 2 and metal 1 are in fact the same, then you cannot measure any voltage. You will find that a 0 voltage will be measured. Let's take a look at an actual laboratory experiment that demonstrates the Seebeck effect. So in this experiment, the TE device is as shown by the cursor. It's situated between a heat sink and a hot plate. The heat sink would maintain the temperature of the cold side to be the same as the room temperature, which is 25 degrees C. And as shown by the display on the front here, the temperature of the hot plate is at 80 degrees C. And we can see the thermal effect, the thermoelectric effect, because if we look at the multimeter on the right side, it is registering 345 millivolts, or 0.35 volts. So in this experiment, the temperature difference delta T is 55 degrees C, and the voltage difference is 0.35 volts. So we can use the definition of the seeback coefficient, and we can calculate the seeback coefficient to be 6.36 millivolts per Kelvin. So notice that the value or the magnitude of the seeback coefficient is in fact quite small. Let us now move on to the seeback effect in a semiconductor. On this page, we have two semiconductor. The first one is a p-type semiconductor. This is the one drawn at the top, and below that we have an n-type semiconductor. And again, the left hand side is hot and the right hand side is cold. For the case of the p-type semiconductor, the carriers are the holes. So just like the case for the conductor, the more energetic holes on the hot side will diffuse towards the cold side. So again, in the steady state, we build up a concentration of holes on the right hand side of the p-type semiconductor, and because of that there will be an electric field which will oppose the further migration or diffusion of holes from the hot side. So in other words, in the steady state, the right hand side of the p-type semiconductor has a net positive potential relative to the left hand side. We can use similar reasoning to understand what happens to the n-type semiconductor. In the n-type semiconductor, the charge carriers are electrons, just like the conductor. And again, because of the conduction of heat through the n-type semiconductor, we have a net diffusion of electrons from the hot side to the cold side. So in the steady state, we will again have a buildup of electrons on the cold side, and this will set up an electric field that will oppose the further diffusion of electrons from the left side to the right hand side. So now we have a net negative potential relative to the left hand side for an n-type semiconductor. Now let us consider connecting the left hand side or the hot side of the p-type semiconductor to the left side of the n-type semiconductor. In other words, if we simply connect these two sides, by an electrical short. And let us consider connecting the positive side of this p-type semiconductor to one side of a resistor, and then the negative side of this n-type semiconductor to the resistor. The result will be a thermoelectric device as shown in this schematic diagram. So in this schematic diagram, the two semiconductors are in fact connected electrically in series, because as you can see, this is a piece of metal forming two contacts with the p-type and n-type semiconductor, and here is another metal contact connecting the p-type and n-type semiconductor to the heatsink. So with this two semiconductors connected in series electrically, but thermally in parallel, what will happen is this: when the hot side is maintained at a higher temperature than the heatsink, heat will flow through the p-type and n-type semiconductors from top to bottom, and the sum of the two thermoelectric voltages across the p and n-type semiconductors will add because of the series connection, and the net thermoelectric voltage will drive a current through the resistor. Now, in order to get a significant current flow, we would like to have a stronger seeback effect. So clearly we need to have a larger seeback coefficient. We would like to have a larger seeback coefficient because this will give us a larger voltage difference for the same temperature difference. In practice, the seeback coefficient is not the only property that affects the efficiency of a TE device. There are two other important properties. The first one is the electrical conductivity, and the second is the thermal conductivity. This comprises the thermal conductivity of the electrons and the thermal conductivity of the phonons. What we want is a high electrical conductivity and a low thermal conductivity for a good TE material. And we can define a figure of merit for the TE device.